Hi friends, to understand the concept of complementary shear stresses, let's take a very simple example. We have got a block having a square section. This length is L, let's say. This is also L, friends. We have got a square section block and it has some width, so let's say width is B. Okay, like this we have. Now if I apply shear stress on this particular surface, okay, let's say the bottom face of this particular block fixed. So if the bottom of this particular block is fixed, so due to application of tangential force over here, so there is a shear stress going to act on this particular surface. So tangential force will produce shear stress over here, and that shear stress I have shown over here. So when you apply shear stress over here in this direction, because this block is in equilibrium condition, so at this particular surface, which is the bottom face of this particular block, will have a shear force, okay, in the reverse direction. So there will be shear stress acting on this particular face in the reverse direction, in the opposite direction, something like this. Okay, so now we have got, friends, a shear stress acting over here, and to balance that shear stress, there is a shear stress acting on this particular face, that is this one. Okay, now these two shear stresses, which are caused due to shear forces acting on these two faces, will produce anti-clockwise moment, right? So it means this entire block will be under anti-clockwise moment now, but this block is going to be in the equilibrium condition. So to balance this anti-clockwise moment, there has to be one clockwise moment acting on the block to make the block in the equilibrium condition. Okay, so that is why you will see shear stress acting on these two faces, something like this. So you will be seeing shear stresses acting on these two faces in the reverse direction like this. Okay, in order to balance the moment caused by these two shear stresses. Okay, so these are called as complementary shear stresses. Okay, once you apply shear stress over here, this shear stress will transform into this kind of system of shear stresses acting on the faces. So these are called as complementary. Okay, to this is the complementary, and to balance these two, these are the complementary. Okay, so this is called as the complementary shear stresses. Mind it, we have only applied shear stress over here, and as a result of it, we got these shear stresses acting on the face of this particular block. So now we would like to find the stresses along the diagonal of this particular block. Okay, there are this diagonal as well as this diagonal. So we are interested to find out how much stresses are going to act along this diagonal. Okay, since we have considered a square block, so this angle is going to be 45 degree. This angle will be 45 degree, friends. Okay, as I have shown here. So diagonal is going to make 45 degree with this particular face. So this is the shear stress acting on this particular face. The shear stress acting along the diagonal, this diagonal, let's say, what I will do is I will first convert this shear stress which is acting over here into the force. So this is shear stress. I will convert this into force. To convert this into force, so to convert this into force, I will have to multiply this by the area of this particular face. So the area is going to be L and the thickness is B, L into B. So L into B we got. Similarly, I can convert this also, which is a shear stress, into force by multiplying this with the length and the vertical thickness, so into L into B. If I multiply this with L into B, now this is going to be a force and this is going to be a force. So we have got a force acting like this, friends, and we have also got a force acting vertically like this. This is a force, friends, which is shear stress into LB. This is also force, shear stress into LB. Now I want to resolve these two forces along the diagonal. So if I resolve this, this angle is going to be 45 degree, as we know. So if I resolve this, this is going to be, so one component of this, so this, if I resolve, this is going to be 45 degree, friends, and there also it is 45 degrees. So I'll be getting the component of this is going to be shear stress LB and then cos 45. So this is due to this particular force. Similarly, this also will be resolved like that. So there will be 2 times shear stress into LB cos 45. The one is due to this one and another is due to this one. Okay, so we are able to resolve these two forces along the diagonal. Okay, this is also 45 degree, as we know. So along the diagonal, I am going to get a force which is equal to 2 times shear stress into LB cos 45. That is very important. So we got shear force along the diagonal will be equal to shear stress into LB cos 45 plus shear stress into LB cos 45, because we have two forces. So both I have resolved. Okay, one is due to this one and another is due to this one. So we got these two. forces acting along the diagonal. So now, so that will be equal to, friends, 2 times shear stress L into B cos 45. Now cos 45 is nothing but 1 over root 2. So the finally you will be getting the value as root 2 times shear stress times LB. This is the shear force along the diagonal we got. Okay, so here if you see, this will be under tension. Okay, tensile forces acting along this diagonal. Similarly, if you see these two, they are going to cause compressive stresses along the diagonal over here. So that is what it is going to work. So if you look at here, this diagonal will be under tension and this diagonal will be under compression, because these two forces will cause compression over here and these two forces will cause tension over here. Okay, along this diagonal there is a tensile forces acting, and along this diagonal compressive forces are going to act. Now next part, what we will do is we will take this half portion of this particular block and we'll try to find out how much exactly stress is going to come. Okay, so in the next part what I will do is I will take this much portion only and we'll try to see how much stress is going to act along the diagonal. Okay, so we have got the shear force along the diagonal as root 2 times shear stress into L into B, right? Now what we will do is we will take this much portion of the block and we'll try to find out how much shear stress is going to act along this diagonal. So let's see that. So I have considered this much portion of the block, okay, and on this particular portion I am interested to find out how much shear stress is going to act on this particular diagonal. Okay, so here the force acting on this particular diagonal, and this force we got as root 2 times the shear stress times length times breadth. Okay, this already we have calculated earlier, right? So shear force acting along the diagonal we have got. Now we wanted to find out the shear stress on this particular diagonal. Okay, so how to find shear stress, friends? You know the shear stress is nothing but the shear force divided by the area on which it is acting. So the shear stress, therefore we can say that the shear stress acting along the diagonal will be equal to the shear force, which is root 2 times the shear stress, this shear stress, into L into B divided by area, friends. But the area will be this area I want to find. So area will be, this length is going to be from here to here. This is going to be B. We already know this is going to be B, right? And here if you see, this is L. This is also L. So this is going to be root 2 times L. A simple geometry, friends. Root 2 times L. Okay. So the area is going to be root 2 times L into B. So it is going to be root 2 times, I am talking about this particular area, which is the area along the diagonal. Okay, so area of the section of the block along the diagonal. So it is, the length is going to be root 2L and the breadth is going to be B. So root 2L times B. So if you look at here, I can easily cancel out root 2 LB and LB. So what we get is very interesting, friends. That is shear stress. So it means if you have a block like this and if you apply shear stress over here, the tau is the shear stress you are applying over here, right? So the complementary shear stresses will be set up across all the faces, but along with that you will also have along the diagonal there will be same amount of shear stress going to come, that is tau. So we can say that if you apply shear stress tau over here, so along the diagonal also the same amount of shear stress will be set in. Okay, so here also you will get same amount of shear stress, friends. So this is going to be tensile, as you have seen here. This is going to be tau. This is also going to be tau. And in this direction there is a compressive shear stress will be set up like this, and that is also going to be tau, right? So if you apply on this surface shear stress, the same shear stress will be coming along the diagonal. Okay, so here it will be coming as tensile and here it is going to come as compressive. This is very important point to note. Let me just, suppose we have, so this is a member for example, and if you are applying shear stress over here, the same will be set up over here, and then you will have the same over here, the complementary shear stresses, and like this. And along the diagonal if you see, so if you take a diagonal like this and a diagonal like this, friends, so along this diagonal you will be having a tensile shear stress, the same, and here you will be having the compressive, and here also you will be having compressive shears. Okay, so this is going to be, the stresses acting along the diagonals. Okay, so if you apply tau over here, shear stress tau over here, same shear stress will be coming along the diagonal. There will be tensile and there will be compressive. Okay, so this is how we get stresses along the diagonal. So this is a very important understanding of complementary shear stresses. Okay.